Hello friends, previously we discussed the Faraday's law of induction, which states that if the magnetic flux through an area bounded by a closed conducting loop changes with time, a current and an EMF are produced in the loop, and this process is called induction. Another law which we discussed is Lenz's law, stating that an induced current has a direction such that the magnetic field due to the current opposes the change in the magnetic flux that induces the current. The induced EMF has the same direction as the induced current. Today we shall be discussing that the induction of a current by a changing flux means that energy is being transferred to that current. The energy can then be transferred to other forms such as thermal energy. Then we shall talk about induced electric fields and reformulate Faraday's law. Induction and energy transfers. By Lenz's law, whether you move the magnet towards or away from the loop, a magnetic force resists the motion, requiring you applied force to do positive work. At the same time, thermal energy is produced in the material of the loop because of the material's electrical resistance to the current that is induced by the motion. The energy you transfer to the closed loop plus magnetic system via your applied force ends up in this thermal energy. The faster you move the magnet, the more rapidly your applied force does work, and the greater the rate at which your energy is transferred to thermal energy in the loop. That is, the power of the transfer is greater. Regardless of how current is induced in a loop, energy is always transferred to thermal energy during the process because of the electrical resistance of the loop, unless the loop is superconducting. For example, when switch S is closed and a current is briefly induced in the left-hand loop, energy is transferred from the battery to the thermal energy in that loop. This figure here shows another situation involving induced current. A rectangular loop of wire of width L has one end in a uniform external magnetic field that is directed perpendicularly into the plane of the loop. This field may be produced, for example, by a large electromagnet. The dashed lines in figure show the assumed limits of the magnetic field. The fringing of the field at its edges is neglected. You are to pull this loop to the right at a constant velocity. Flux change. The situation of the figure on the left does not differ in any essential way from the figure on right. In each case, a magnetic field and a conducting loop are in relative motion. In each case, the flux of the field through the loop is changing with time. It is true that in figure on the right, the flux is changing because magnetic field is changing, and in figure on left, the flux is changing because the area of the loop still in the magnetic field is changing. But that difference is not important. The important difference between the two arrangements is that the arrangement of figure on left makes calculations easier. Now let us calculate the rate at which you do mechanical work as you pull steadily on the loop in figure on left. Rate of work. As we will see, to pull the loop at a constant velocity, we must apply a constant force to the loop because a magnetic force of equal magnitude but opposite direction acts on the loop to oppose us. So the rate at which work is done, that is, the power is given by P is equal to F into V. Here F is the magnitude of your force. We now wish to find an expression for P in terms of the magnitude B of the magnetic field and the characteristics of the loop, namely its resistance R to current and its dimension L. As you move the loop to the right, the portion of its area within the magnetic field decreases. Thus, the flux through the loop also decreases, and according to Faraday's law, a current is produced in the loop. It is the presence of this current that causes the force that opposes your pull. Induced EMF. To find the current, we first apply Faraday's law. When x is the length of the loop still in the magnetic field, the area of the loop still in the magnetic field is Lx. Then from equation phi b is equal to Ba, the magnitude of the flux through the loop is phi b is equal to Ba, which is equal to Blx. As x decreases, the flux decreases. Faraday's law tells us that with this flux decrease, an EMF is induced in the loop. Dropping the minus sign in Faraday's equation and using equation A, we can write the magnitude of this EMF as epsilon is equal to d phi upon dt, which is equal to d upon dt of Blx, which is again equal to Bl into dx upon dt, and finally it becomes equal to Blv. Here we have replaced dx upon dt with V. This figure shows the loop as a circuit. Induced EMF is represented on the left and the collective resistance R of the loop is represented on the right. The direction of the induced current I is obtained with the right hand rule for decreasing flux. Applying the rule tells us that the current must be clockwise and induced EMF must have the same direction. Induced current. To find the magnitude of the induced current, we cannot apply the loop rule for potential differences in a circuit because we cannot define a potential difference for an induced EMF. However, we can apply the equation epsilon is equal to Ri or I is equal to epsilon upon R. With equation B, this becomes I is equal to Blv divided by R. Because three segments of the loop in figure carry this current through the magnetic field, sideways deflecting forces act on those segments and they are marked as F1, F2 and F3. Note however that from the symmetry, forces F2 and F3 are equal in magnitude and cancel. This leaves only force F1, which is directed opposite your force on the loop and thus is the force opposing you. So F is equal to minus F1. Using equation Fd is equal to ILB into B, we obtain the magnitude of force, and noting that the angle between magnetic field and length vector from the left segment is 90 degrees, we write F is equal to F1, which is equal to ILB sine 90, which becomes equal to ILB. Substituting equation C for I in equation D then gives us F is equal to B square L square V divided by R. Because B, L and R are constants, the speed V at which you move the loop is constant if the magnitude F of the force you apply to the loop is also constant. To find the rate at which you do work on the loop as you pull it from the magnetic field is found by substituting equation E in equation 1, that is P is equal to Fv, which is equal to B square L square V square divided by R. To find the rate at which Thermal energy appears in the loop as you pull it along at constant speed. We calculate it using this equation: P is equal to I square R. Substituting for I from equation C, we find P is equal to BL upon R whole squared into R, which becomes equal to P is equal to B square L square V square divided by R. This is exactly equal to the rate at which you are doing work on the loop. Thus, the work that you do in pulling the loop through the magnetic field appears as thermal energy in the loop. Eddy currents. Suppose we replace the conducting loop with a solid conducting plate, and we then move the plate out of the magnetic field as we did with the loop. The relative motion of the field and the conductor again induces a current in the conductor. Thus, we again encounter an opposing force and must do work because of the induced current. With a plate, however, the conduction electrons making up the induced current do not follow one path as they do with the loop. Instead, the electrons swirl about within the plate as if they were caught in a whirlpool of water. Such a current is called an eddy current and can be represented as it is in figure A, as if it followed a single path. As with the conducting loop, the current induced in the plate results in mechanical energy being dissipated as thermal energy. The dissipation is more apparent in the arrangement of figure B. A conducting plate free to rotate about a pivot is allowed to swing down through a magnetic field like a pendulum. Each time the plate enters and leaves the field, a portion of its mechanical energy is transferred to its thermal energy. After several swings, no mechanical energy remains and the warmed up plate just hangs from its pivot. Induced electric fields. Let us place a copper ring of radius r in a uniform external magnetic field, as in figure shown here. The field, neglecting fringes, fills a cylindrical volume of radius r. Suppose that we increase the strength of this field at a steady rate, perhaps by increasing in an appropriate way the current in the windings of the electromagnet that produces the field. The magnetic flux through the ring will then change at a steady rate, and by Faraday's law, an induced EMF and thus an induced current will appear in the ring. From Lenz's law, we can deduce that the direction of the induced current is counterclockwise. If there is a current in the copper ring, an electric field must be present along the ring because an electric field is needed to do the work of moving the conduction electrons. Moreover, the electric field must have been produced by the changing magnetic flux. This induced electric field is just as real as electric field produced by static charges. Either field will exert a force on a particle with charge. By this line of reasoning, we are led to a useful and informative restatement of Faraday's law of induction, that is, a changing magnetic field produces an electric field. The striking feature of this statement is that the electric field is induced even if there is no copper ring. Thus, the electric field would appear even if changing magnetic field were in a vacuum. To fix these ideas, consider this figure, which is just like figure A, except the copper ring has been replaced by a hypothetical circular path of radius r. We assume, as previously, that the magnetic field is increasing in magnitude at a constant rate. The electric field induced at various points around the circular path must, from the symmetry, be tangent to the circle. Hence, the circular path is an electric field line. There is nothing special about the circle of radius r, so the electric field lines produced by the changing magnetic field must be a set of concentric circles as in figure C. As long as the magnetic field is increasing with time, the electric field represented by the circular field lines will be present. If the magnetic field remains constant with time, there will be no induced electric field and thus no electric field lines. If the magnetic field is decreasing with time at a constant rate, the electric field lines will still be concentric circles, but they will now have the opposite direction. All this is what we have in mind when we say a changing magnetic field produces an electric field. A reformulation of Faraday's law. Consider a particle of charge Q0 moving around the circular path. The work done on it in one revolution by the induced electric field is W is equal to epsilon Q0, where epsilon is the induced EMF, that is, the work done per unit charge in moving the test charge around the path. From another point of view, the work is W is equal to integral of f dot ds, which is equal to Q0e into 2 pi r, where Q0e is the magnitude of the force acting on the test charge and 2 pi r is the distance over which the force acts. Setting these two expressions for W equal to each other and cancelling Q0, we find that epsilon is equal to 2 pi r into E. Next, we write equation F to give a more general expression for the work done on a particle of charge Q0 moving along any closed path, that is, W is equal to cyclic integral of f dot ds, which is equal to Q0 into cyclic integral of E dot ds. The loop on each integral sign indicates that the integral is to be taken around the closed path. Substituting EQ0 for W, we find that epsilon is equal to cyclic integral of E dot ds. Meaning of EMF. With equation G, we can expand the meaning of induced EMF. Up to this point, induced EMF has meant the work per unit charge done in maintaining current due to a changing magnetic flux, or it has meant the work done per unit charge on a charged particle that moves around a closed path in a changing magnetic flux. However, with figure B and equation G, an induced EMF can exist without the need of a current or particle, that is, an induced EMF is the sum via integration of quantities E dot ds around a closed path where E is the electric field induced by a changing magnetic flux and ds is a differential length vector along the path. If we combine equation G with Faraday's law, we can rewrite Faraday's law as cyclic integral of E dot ds is equal to minus d phi b upon dt. This equation simply says that a changing magnetic field induces an electric field. The changing magnetic field appears on the right side of this equation, the electric field on the left. So friends, here we come to the end of our discussion in this lecture today, and therefore we sum up. An induced current has a direction such that the magnetic field due to the current opposes the change in the magnetic flux that induces the current. The induced EMF has the same direction as the induced current. The induction of a current by a changing flux means that the energy is being transferred to that current. The energy can then be transferred to other forms such as thermal energy. So that is it for today. See you in the next lecture where we shall be discussing about self and mutual inductance. Thank you very much.